Lesson 6.2, inverse relations and functions. So if two functions or relations are inverses of each other, that means that if y equals f of x, that x equals the inverse function of y, right? We can say that all the x and y values swap places. Right? There's some function interpretations that I'll walk you guys through, examples. Right? There's a graphical way to interpret this. Right? And you can also interpret inverses through tables of values. So some real life examples could be like, there are different temperature systems. There's a Fahrenheit versus a Celsius system. Okay, what if you, in your mind, know how to read Celsius and you vacation to the United States where we're reading everything in Fahrenheit? Can you have some function to convert Fahrenheit into Celsius, right? And then the inverse of that, the theme of this lesson, the inverse would be the other way around, right? So what if you're an American who's familiar with Fahrenheit and you vacation over in a country where they're using Celsius? You say, oh, it's a jolly 22 degrees outside. And you're like, wait, what? Right? Can you convert that back into Fahrenheit? And these two functions would be inverses of each other. You can go Fahrenheit to Celsius or Celsius back to Fahrenheit, right? Another example I'll do with you guys is how about what's the volume of the cylinder as a function of its radius? Right. So if you know the radius, you know the length, then you could calculate the volume. Right. But you could go the other way around. What if you fill it with water, pour out the water, measure the volume of the water, so you know that? It's like, hey, I wonder what was the radius of the cylinder. Well, now volume to radius or radius to volume, well, those could be also inverse relationships. Right. Okay. And then I'll do a bunch of other examples with you guys. All right. So back to the beginning. Right. So two relations are inverse relations. If one relation contains elements in the form AB, where is the other relation contains elements in the form BA. So you can just swap all the x and y values, right? Um, Two functions f and g are inverses if and only if both their composites are the identity function. The inverse function f of x can be written as f negative one x. Right. So see where I put this subscript negative one. Right. That's not a power negative one. It's just notation to designated inverse function, something like that. Right. Now, when they say their composites are identity function, that means if you find f of g of x, here, I'll write this out, and maybe we'll test this later, right? Because there's a lot of cool little tricks that you can do with inverses, and this is one of them, right? If f of x and g of x are inverses, inverse or have inverse relations, right? Right. That's to say, uh, f negative one of x equals g of x, and vice versa, right? Something like that. Right? Then okay. If I take f of g of x, I should just get x, and vice versa. If I take g of f of x, I should also get x. Now, the last lesson we were looking at, we were doing composite functions, like take f of g of x and so on, right? And if you do f of g or g of f, we were getting different outcomes. But this would be an exception to that. So if two relations are inverses, then if you take one function of the other function, you should get exactly x both ways. Teachers, day for it. All right, so we got next here. So example one, right, we've got a graph, an expression, and a table. All right, so let's tackle all these. Right? Right. Okay, not all functions have an inverse function. You might have an inverse relation, but remember, a true function has to pass the vertical line test, which won't always happen, right? And so determine, okay, let's find inverses. So, all right, 1A looks like, here, I'll try to copy down this graph best I can. Okay, we got x-axis and a y-axis. So we got x and y. Okay. So let's get some coordinates on here. This goes to the point 0, 3. So right there, 0, 3. Okay. It also goes through, well, actually, you know what? It misses a little bit. Well, okay. It goes kind of close though. Okay. Over 2 up 1. I'll get a function that's really similar to it. Okay. Okay. Go down 1 back 2. Okay. Just keep going like that. Okay. So there's this linear relationship. This linear relationship. Okay. Okay, so it's a little bit off from the example, but it's plenty close enough to get the idea. Okay. So do you guys see that this point right here is 0, comma 3? And this point right here could be 2, comma 4. And this point right here could be negative 2, comma 2. negative 2, comma 2, right? Right, and we have a linear relationship that goes through all those, right? Well, if you want to find the inverse, all you have to do is swap all the x and y values. So instead of 0, 3, what if it had 3, 0? Right? So that could be a point on the inverse graph is 3 comma 0. Right? How about 2, 4? Well, I can make that 4, 2. So 4, 2 is right about here. Right, so that looks like 4 comma 2. Okay, and then negative 2, 2. Well, the inverse would be 2 comma negative 2. So that's 2, negative 2 is like right here. Right? And oh, look at that. All these points also lie on a straight line. Okay, so that's interesting. Like this. Okay. So if this original function was f of x, then this one I just wrote pink could be the inverse. And I could write it this way, f negative 1x to designate the inverse. Right, you said. Right. Right. How about this? There's a couple of things I'm going to do with this graph. Let's come up with an equation for each of these. And I'm going to show you guys that what I wrote back here will work. Right. Right. So this could be y equals mx plus b. This has a slope of up 1 over 2, so 1 half x, and then a y-intercept at 3. Okay, so that's this expression. Okay, how about this pink expression? What would this be? Okay, so, well, if I continue back down, this is back 1 down 2, back 1 down 2 again would bring you down here. Okay, and then back 1 down 2 again would bring you down here. So that's negative 2, 4, 6. This is negative 6. So this has a y-intercept at negative 6, and it has a slope of up 2 over 1. So this would be 2x and then minus 6. Okay, so that's the equation of the inverse. Right? Now, I got that just off the graphs. Right, so all I did was I reversed the x and y coordinates. That's how I took these 3 coordinates and turned them into these 3 coordinates. Right? And I just found the lines that go through this. Right? Now, let's see, how can I get that systematically? So I want to show you guys that if you just had this equation, you could still, if I gave you this black equation and said find the inverse, you could still get this pink equation systematically by just swapping the x and y. So watch this. What if I do y equals, instead of x, I'll call it y, then 1 half x plus 3. So a good way to take an inverse, and I'll spell out inverse here, inverse function or relation, but this will be a function, okay, is just to swap the x and y. So where the y goes, put x. And where the x goes, put y. I mean, that's all I did with the coordinates, isn't it? I just, like, 0, 3 became 3, 0, and so on. I just swapped the x and the y. Okay? So now solve for the new y. And I guarantee you I'm going to get this p expression right here. Let's try it out. Let's see, subtract over 3. So it'd be like x minus 3 is 1 half y. Okay, I'll swap both sides while I'm at it. So 1 half y equals x minus 3. Okay. And then I can multiply both sides by 2. So times 2 on both sides, balance the equation. So since out here, I'm getting y equals. Then I distribute this 2, boink, boink. That's 2x, and then distribute 2, that'd be minus 6. Right? Now, instead of y equals, because that was my original expression, I could call this f inverse x, but because I did just find this inverse function. So everything inverse function and down is the same expression. I get 2x minus 6. Is that the equation of my pink line? Like if this black line was the original function. Is the inverse really 2x minus 6? Is that what we got? Yeah, that's exactly what we got. It's the same thing. Look at that. Look at that. Right? I also promised I'd show you guys that this is true. If you take f of g or g of f, both cases it should turn out to be x. So I have these two expressions I just showed you guys systematically that one leads to the other, both graphically and algebraically. Okay. Let's find f of f inverse of x. I wonder what is that? Well, f of something is 1 half of that something plus 3. Okay. And the something in this case is the inverse function, which is 2x minus 6. So let's play this out. Okay. So see, it's 1 half can distribute. That'd be half of 2x is x, and then half of negative 6 is negative 3, and then plus 3. Oh yeah! Look at that! Equals x, just like I promised you guys it would be. It totally is, right? Let's try it the other way around. Because remember, last lesson, g of f and f of g could come out to be different things, but in this case, I'm telling you they should be the same thing. So what if I take the inverse of the original function? Right? Will I still get x? So the inverse function is here in pink. So that's 2 times something and then minus 6. Right? And the something in this case is the original expression of half x plus 3. Half x plus 3. Okay, so let's play this out, see what happens. So I can distribute this 2. So 2 half x is just regular x. I get a plus 6 and a minus 6. Oh yeah! Look at that! That's also x. Different way to get there, but all right, so both ways, right? So if you take the function of the inverse function or the inverse function of the original function, either way, have to get x. Right? So get that. And one more thing I want to show you guys on this graph example before I move on, because there's a ton of cool tidbits you get out of this. If you make a 45-degree line, so we can call this the line y equals x. Okay, see, this is the line y equals x, right? So y equals x, right? Which the inverse of y equals x is x equals y, which is the same line, right? So wouldn't the inverse of this line just be itself, right? And that's the only line that works out that way. Okay, so the inverse of y equals x is y equals x. Okay. Well, if those are the same, think of this being sort of like a mirror. And do you guys see that these two functions, this black function, this pink inverse function, sort of reflect over that mirror? Okay. So another way you can get an inverse function is you can say if you had that original black line function right there, I wonder what the inverse is. Right? You can pick up the paper, you can hold the top right and bottom left corners of the paper, and you can rotate the paper over that line and then look through the paper. Right? So here's my new x-axis. You can see it through the paper. Here's my new y-axis. Right? And then the original function now takes the place of the inverse. Hey, and the inverse, well, the inverse of the inverse is back to the original function up here, isn't it? Right? Let me show you guys. I'll do it one more time, but I'll make these lines bolder so they're easier to see. Right, so go over this in blue marker here. Right, so I'll mark out my axes. Right, so that when I look through the paper, I'm looking through the paper trick. I can more easily see that these are going to stand out. There's my well, it's x, y on this side, but that's going to reverse on the other side. Okay. Right, here's my 45-degree line, dash, 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 dash. Right, then I'm going to flip it over. Okay. Here's the inverse function. And here's the original function. Right? And again, make it really bold with the marker so that I can see it more easily through the paper when I do the turn the paper trick. Okay? And because going from the original function to the inverse, it's kind of like reflecting it over y equals x. Okay? So I'll do that again, just like I did before. So grab the top right and bottom left of the paper, then rotate it about that 45-degree line. And oh yeah, now it's even more obvious that what was the original function becomes the inverse, and what was the inverse becomes the original function. Here's my new x-axis, my new y-axis, and it's all inverted. Yeah, it's all there. It's all there. So flip the paper trick is pretty cool too. Okay. Okay, so yeah, there was a lot embedded in that one I want to show you guys. Okay. Okay, how about the next one? So 1b says determine whether the inverse is a function. Oh, actually, that's what we're supposed to do for all these. But here, I think each of these lines passes the vertical line test. So yes, those would also be functions. Okay. Okay. But this one would be a parabola. If they're giving us y equals, we can say f of x if you like, 2/3 x squared minus 4/3. Okay. And I know what basic shape it's going to be. Like if I plug in 0 for x, I would get negative 4/3 for y. So here, just as a general idea, I'll put some point that could be negative 4/3. Okay. And it's just going to be a parabola that opens upward, doesn't it? Right, parabola opens upward. Right. Okay. Now, here, let me show you guys the flip the paper trick on this. So I'll make the axes really bold so they show through. So my y-axis is about to become my inverted x-axis and vice versa. Right, and then make my parabola really bold right here. Really bold parabola, like this. Okay. Okay. Now, if I flip this over the y equals x line, so this is y equals x, right? And I look through the paper from the other side, having flipped it over this line, it will tell me what the inverse relation is. Notice I'm saying relation because watch this. If I flip this, ooh, here's my new x-axis, my new y-axis. See how I have a sideways parabola, which definitely fails the vertical line test. Fails the vertical line test. There's 2.3. So that would no longer be a function. Now, it could be a relation, but not a function. How about algebraically? Algebraically, all I have to do is swap the x and the y and solve for the new y. Okay? So I'll label this inverse. I'll call it relation because again, I know it's going to not be a function. I can say x equals 4/3 y squared minus 4/3. Solve for this new y. What am I going to get? Okay, let's try that. Okay, so I can add over 4/3. So that's 4/3. So this was 2/3. I don't know why I just did that. Okay, that was just trying to copy this here. There we go. All right, so now we're back. Now we're back. Okay. Of y we're solving for squared equals x plus 4/3. Right? Then multiply both sides by 3/4. So times 3/4, and over here times 3/4. Okay. Right, to do that, right? So I'm getting y squared is, and then distribute those 3/4. That looks like 3/4 x plus, and this would just become 1, right? Because 4/3, 3/4 makes 1, right? Now you could stop there and interpret that, or you could go one more step and say y equals, now it'd be square root of all this stuff, 3/4 x plus 1, okay? But the fact that we took the square root ourselves, this comes out to plus or minus. Hence, right, if I look at the, say, here's the original graph. Remember the inverse, if we just flip it over that line, right? Okay, right. Now if I only had the plus interpretation, that would just be the top part of this curve. And if I do the plus or minus, then I get the top and also the bottom, which makes it fail as a function, but can still be a relation. Ah, right. Ooh, here's another thing I see. I see this +1 would have shifted the whole thing to the left. You can see that too, because here's kind of my ghost y-axis. This whole thing is shifted to the left, right? Shifted to the left one, yeah, or something like that, right? I have to factor out the 3/4 to say how much is it shifted to the left, right? Which would be 3/4 plus 1. Yeah, so there's your inverse relation right there. Okay, so that would not be a function. How about this table of values? Right, so you can see this table of values, right? We have an x and a y here. Maybe I'll draw this out. Make it really obvious. Right. So we don't have maybe a full graph going on, but we do have some points, and we can make some sense of the story. So x goes from -7 to 1. 1, 2, 3, 4, 5, 6, 7. There's -7. Here's 1. Okay. And the y values, ooh, well, those are really tiny. Okay, let's kind of spot them somewhere. Like this was 1, this is -1. Whatever. Okay. And so -7, 1.25 could be right here. Okay. -5, -100, basically. Okay, that's like right here. Okay. -3, and then a tiny, tiny, tiny bit. Right? I don't know where are they pulling from some real life example? These are some weird numbers. 0, 0. Right? And then 1, negative something. Okay. Okay, that's it. Okay. Now, the original set of values does work as a function, or at least it doesn't fail as a function, because it passes the vertical line test if I pass a vertical pen over or a ruler, right? Every x value corresponds to one y value. That's okay. Okay. But the opposite is not true. Does it pass the horizontal line test? Well, no, because these 2 points right here have the same y value. They're both -0.0125. At this x value, -5, this x value, +1. Right? They have the same y value. So it fails the horizontal line test, which means that when I swap all the x and y and make an inverse relationship, that would fail the vertical line test. Right? Let me show you guys the rotate the paper trick. So, well, I have writing on the other side of this paper, so when I flip the paper, just ignore the writing that's there. But you're trying to see through. Okay. Here, you guys see where my x-axis is? That's about to become the y-axis when I rotate this. Okay, and watch these 2 points. They're going to both exist on the same vertical line. So if I flip this, you're looking through the paper. It's okay. So I'm looking through the paper, those dots, right? They would lie right on top of each other. Okay. Right, so any function that fails the horizontal line test, it is still okay as a function itself, but its inverse relationship would no longer be a function. All right. So I think that's plenty good on that. Got next. Example 2. Inverse functions for, okay, example 2. We got for f of x is 3x plus 2. Okay, what do they want us to do with this? Determine whether the inverse is a function. If it exists, graph the function and its inverse. Yeah, we can do that. So for inverse, what I would do is swap the x and the y. So x equals 3y plus 2, and then solve for the new y. Right? So subtract over 2. So 3y equals x minus 2, and then divide both sides by 3. So y equals 1/3 x minus 2/3. Right? You could also call it f inverse of x. Oh yeah, this will be a function. It's just linear. Anything that's linear should come out to be a function, unless it's like a vertical line. Okay? So there's the inverse function. Okay? So let's graph both of them, the original function and the inverse function. Okay? And they should carry that same pattern that you saw before. Like they should be able to mirror over the y equals x 45-degree line. Okay, so let's see if that's true. Okay. So there's my x, there's my y. In fact, I'll go ahead and get that 45-degree line started ahead of time. Okay. There's y equals x. So you can think of this as a mirror. between the original and the inverse function. Right? Now 3x plus 2. I'll go up 2, right? And then if I go, so there's a point there, it's y-intercept. If I go up 3 more and then over 1, that's a point. Or if I go down 3, back 1, that could be a point there, just like right there. Okay. So here's the original function. So I'm drawing that original function in black. Okay. Okay. Ooh, here's something that we didn't quite run into with the previous example, okay, is I did draw this line to the point where it does cross my 45-degree y equals x line, okay, which means that when you swap x and y, and this would be the coordinate right here, or I'll point out this coordinate, is at -1 comma -1. Okay. That should also be true for the inverse. The inverse, if I swap -1, -1, I still get the same point as itself. So I bet the inverse relation also goes to that point. Okay. And let's go ahead and graph that now. Here, I'll do this in pink. So 1/3 x minus 2/3. Now minus 2/3 is right here. So there's the y-intercept. And this has a slope of up 1 over 3. So up 1 over 3, and then up 1 over 3 again, brings me through here. Or go down a third and back 1. Goes exactly through that point, just like I told you guys it would. Yeah, yeah. So it goes like this. Okay. And there's the inverse relationship. So if this dark black line here is f of x, then this pink line is f inverse of x. And look at that. They do mirror over that 45-degree line, just like I told you they would. Right, and they cross right over at the same point. Yeah, just like they should. Just like they should. Oh, good. Oh, you know what? Your book has the answer right here. Here it is. Yeah. So what I drew and what they came up with is same picture. Same picture. Okay. All right. Example 3, inverses with restricted domains. Ooh, right. You can see right away that, well, there's going to be a special issue that pops up. So example 3, right? F of x is x squared. Okay, guys, as soon as you hit x squared, now we have a parabola. I think you guys saw that before. Is that its inverse? Well, it's not going to be a function unless you cut off half of the story, right? Then you could do something like that, right? I think I remember seeing some Alex questions like that. They said, well, only include the part that would actually make the inverse a function. Right? So now what? And of course, all these examples, your book tells you exactly what to do. And it's what I was going to say anyway, exchange x and y. That's what I've been doing all along. Okay. So for the inverse, I'll say x equals, and then do y squared plus 2y plus 4. Okay. And then solve for this y. Right? So all I did was exchange x and y. This was y, now it's x. These were x, and now they're y. Right? Now solve for y. So now what? Um, well, okay. I could apply a quadratic equation. Right? If I subtract over x, I could set that up. Right? Or I could do what's called completing the square. Right? You guys remember completing the square? Right? So here, give it some space here. Right? So I want y plus something. I need to square this so that it creates the original function. Right? And the 4, hang on to that. Right? So what can I do here? Well, I need something so that if I FOIL this out, I get a coefficient of 2 on this y. And the only number that'll do that is 1 with this completing the square. And I'm going to spell this out. Complete the square. Right? Not the only method, but probably a pretty good method for what we're doing here. Right? Now, if I work backwards, I have to make sure that what I have matches what I had before. Like it's all consistent. So I get y times y is y squared. That's good. 1y and y, 1y is 2y. If I'm foiling this out, that's good. And then I get 1 squared, which is 1, which doesn't quite match the 4. So it's kind of like I have a 1 here in excess. So I need to do plus 3 so that the plus 1 I get here combined with this plus 3 brings me back to this plus 4. Right? Or what your book did, they may have thrown in a middle step. Yeah, they did right here. They went ahead and subtracted this 4 over to the other side to get that alone. And then they did a plus 1, and then they restored it with a plus 1. So there's a few different ways to navigate this. But what's really important is you want to make sure that this step is consistent with the previous step. And if you're not sure, you can FOIL all this out and make sure that it does go back and it's all consistent. Okay, this is, I'll say this one again. Okay, this is y squared, bing, that's good. Plus y, there's my 2y, bing, plus 1. And if I take that plus 1, which is already embedded with this, and add it with this 3, that is consistent with this plus 4. Bing, it's all there. Right? Okay, so now look. I'm still trying to get y. So maybe that was probably the hardest step in this. And the rest of this is just regular algebra. I can subtract off the 3. So get y we're solving for plus 1 quantity squared is x minus the 3. So I subtracted the 3 over. Okay. Square root both sides. So y we're solving for plus 1 equals, okay, now here's where it gets tricky. Because if I just do square root of x plus 3, well, what do we mean exactly by that? Now, the fact that we took the square root ourselves, there's actually a plus or minus that pops up here, right? Which would make it no longer a function. It could be a relation that's not a function. So if I want this to be a true function, I would have to consider traditionally you just do the plus half of this, right? Unless maybe there's a special word problem where you have to do the other interpretation, but typically you just do the positive half. Is that what they did? Okay. Now they have the graphical example here. Now here's the original function, which I told you was going to be a parabola. Right? They have this right here. Right? Now, if they take the plus or minus after I subtract this one over, then you get this full sideways parabola. But if you only do the plus part, you get this sort of maroon top half. If you only do the minus part, you get this orange half down here, which by themselves could each be functions, but not both of them together. Right. So here, next thing I'll do is I'll just subtract over 1. So f inverse x is my new y, which is well, -1. And then if you do plus or minus, you get both the top and the bottom of the sideways parabola here. Right. So just plus is the maroon top, just the minus is the orange bottom. If you do plus or minus, that's where you get both, and it's a relation that's not a function. Things like that. Okay, example 4. Interpret inverse function. Okay, here's that Celsius Fahrenheit example that I was pointing out earlier. Right? So formula for converting temperature in Fahrenheit to Celsius. Right? So this is like example 4. Right? Say you're coming from a foreign country and you know how to think in terms of Celsius, and you come to the States. Right? And they say, oh, the temperature is a nice like 76 degrees outside. You're like, wait, what? What does that mean? Right? So temperature as a function of x, where x could be the degrees in Fahrenheit, could be you take 5/9 of the temperature in Fahrenheit and subtract 32. Okay, so x is 10th in Fahrenheit. I'll abbreviate that. Okay. And this is temperature in Celsius. Celsius, like that. Okay. So you go from Fahrenheit to Celsius. Okay. Now the inverse would be the flip story. What if you're an American? You know how to think in Fahrenheit, and you travel to a country where they're reporting everything in Celsius, and then you'd want to solve exactly the inverse, right? So we can do that too. That's it. So what if here I'm going to change this notation, right? So this is how I do some physics. I say temperature in Celsius is 5/9 times the temperature in Fahrenheit minus 32. Okay, this looks easier than like X and wait, what? Okay, so it's better. So it's the same thing. Now, what if I want to solve for the temperature in Fahrenheit, right? So I can just do that. So multiply both sides by 9/5. So temperature Fahrenheit we're solving for minus 32. I'm going to multiply both sides. Here, I'll write that in pink. Times 9/5 on this side times 9/5 on this side. And then that gives me 9/5 of the temperature in Celsius, whatever that's reported as. Right, then simply add 32. So the temperature in Fahrenheit would be 9/5 of the temperature reported in Celsius, and then you just tag on 32, and that's your temperature. Right? I bet you guys know at least one value that corresponds. Do you guys know that 0 degrees Celsius is 32 degrees Fahrenheit? That's the point that water freezes. Okay? So if you plug in 0 for Celsius, times 9/5 still 0, plus 32, yeah, that is 32 degrees Fahrenheit. So let's try those examples that I was saying earlier. Wait, like what if they say, like, oh, it's 23 degrees outside, but you're in a foreign country. Right? What would that be in Fahrenheit? Actually, that would be this here. So you take 9/5 times just 23 degrees outside, and then plus 32. You say, oh, that's about 73 degrees Fahrenheit. Pretty close. Okay? Or what if you're taking a trip to the States and they say it's 76 degrees outside? You're like, wait, what does that mean? So that could be more like this right here. You say, okay, I'm going to do 5/9 times 76 minus 32. And then you say, oh, 24 degrees. And then if you grow up learning Celsius, then that would make more sense to your mind. Yeah, so you can go back and forth. You got Fahrenheit to Celsius, Celsius back to Fahrenheit, just like that. Those are inverse relationships. All right. Use compositions to verify inverses. Okay, this is what I did with you guys earlier. Example 5, okay, where I said if you take f of f inverse of x, you should get x, and vice versa. If you take f inverse of f of x, you should also get x. So let's do their example here. They're saying h of x is square root of x plus 13, and k of x is x minus 13 quantity squared. Right? Now, are those inverses? Well, let's take one function of the other function and see if it comes out to x both ways. So what's h of k of x? Maybe I'll start with that one. So h of something is the square root of that something plus 13. Right, guys, yeah, that's like the model for h of something. Square root of something plus 13. Now, the something in this case is not x anymore. It's k of x. And k of x is x minus 13 quantity squared. Okay, so now that's what fits under. And it takes that space. So h of k of x then is, okay, yeah, I don't see. I don't think that's going to work. Because if you FOIL this out, that's like x squared minus 13x minus 13x, that's just 6x. Okay. And then that'd be plus 169, wouldn't it? Oh, well, okay. I was kind of hoping they would give us something that actually did work. But this is not x. Okay, I can see that's not going to be x. Oops, this is yeah. Okay. So not inverses. Okay. Do they well, they did give us another example right here, so maybe I'll try that one. Okay, so this failed, okay, but that's okay. Let me try this other example. Okay. So what about f of x is x over 9 plus 4/3, and g of x is 9x plus 12. Let's try those. Okay. So what is f of g of x? And then later on, we'll try the other way. Okay. So f of something is that something over 9 plus 4/3. Okay. And the something this time is no longer x, it's g of x, which is this whole expression right here. And x plus 12. That's what takes the place of x. So now we have f of g of x. So let's play this out. So now I can't simplify this. So 9x over 9 is just x. Now 12 over 9 is, really? Did this one not work out either? 4/3. Okay. Well, that one also fit. This really gives two failing examples. They sure did, didn't they? If they said minus 4/3, this would have worked because this would have given me x. Okay. So, okay, this didn't work either. Okay. So not inverses, because this does not come out to x. Okay, but well, okay, I showed you guys some examples earlier that actually did work. So if you just rewind the video, see, to have my notes within reach here is we through them real fast. Right, so yeah, okay, here we go. Okay, right, so here's some examples I did with you guys earlier, and here's the no, sorry, slightly different graphs. Okay, you guys saw these. Okay, so we're looking at this f of x and this inverse, right? And then, right. Anyway, if you take the f of its inverse and you get x, and it works both ways, right? So f of g and g of f, they could both come to x, and they would be inverses. So that could work. All right, so you guys see some of those. Example 6, verify inverse functions. So example 6. Okay. So here we got the volume of the cylinder as a function of its radius. Okay. Now the volume could be this cross-sectional area, the circle shape, times the length, right? Is it like this 2D base times the length could give you like a 3D volume, okay? Okay, so you're saying let's take 5 because it's 5 inches long. That's what the 5 means, 5 inches, okay? And multiply by the area of the circle, which in terms of its radius is pi r squared. You guys know that, right? Area of the circle is pi r squared. So we got that, right? Okay. Now, what the inverse would mean is not if you want to know what's the volume as a function of radius. What if you want to know the radius as a function of the volume? Right? That's to say, if you fill this with water and then pour that and measure the water, then you would know the volume. Okay? And then if you know this is 5 inches long, you say, huh, I wonder what is the radius of the circle? Well, I can calculate that because I can solve this here. And that's like inverse, an inverse relationship. Not b is a function of r, but r is a function of b. So let's do it. Let's do r squared, solve for r, equals, well, I could take this original volume and divide by 5 pi. And then take the square root. So radius is the square root of whatever volume I measure, like volume of water. If I divide it by 5 pi and take the square root, that is the radius. Right? Now, these functions should be inverses of each other. Right? So how can I do that? Right? Or how can I test that? Let's test radius as a function of volume as a function of radius. Okay, I guess that's what we're doing, right? Right, so I should get radius out of this. Let's see if I do. So radius of something is the square root of the volume over 5 pi. Right, so I got all that set up. But I'm not going to put v for volume. That could be anything. I'm going to put the volume in terms of its own radius, which is 5 pi r squared. Right, so be like that. Now I see right away the 5 pi cancels. And now I have the square root of r squared, which is r. Square root of r squared is r. Bing. Yep, that's definitely inverse. What if I take the volume of the radius as a function of volume? Like that. Well, the volume of something, that's what we started with, is 5 pi radius squared. But I'm not going to write radius for the radius. I'm going to say radius as a function of volume is the square root of volume over 5 pi. Okay, and that's what's being squared. Right? Let's try that. So that's 5 pi times, no, the square root of the volume being squared is the volume. And then 5 pi square root squared is also 5 pi. And oh, look at that. Right. That just leads back to the volume. Right? Yeah, so the fact that these two relationships are inverses, yeah, you take the function of its inverse, right? It just brings you back to the identity variable. Right, so that's all good. Jump into these. For each function, determine whether the inverse is a function. Okay, so I've got this algebraic expression, I've got a table. Okay, let's throw in this table. Right, we'll do that too. Right, and a graph. Right, so the main three types there. Right, so number one, whether the inverse is a function. We got f of x is 2 this, and then x minus 5 being squared. Okay, well, I know right away this is not going to be an inverse. Sorry, the inverse, I should say, could be a relation that's not a function because it would fail the vertical line test. Right? I can show that by graphing this. Okay. Yeah, here, I'll do the algebra first, and I'll graph it later. Okay. So let's find inverse algebraically. So I can swap the x and the y minus 5 squared. Okay. So multiply both sides by 5 over 2, 5 over 2, 5 over 2. That gives me y minus 5 quantity squared equals 5 halves x. Right? That. Take the square root and then add 5. Right? So that is the inverse. So I'll call it f inverse of x equals. Right? Now the tricky thing is the square root could be a plus or minus. I should have done that for that set, plus or minus. Right? Which is going to make it fail the vertical line test. So show you guys that that's true. Right? Got my y-axis and my x-axis. Notice I'm making these really bold. I should really break out the marker for this. Make really bold because I'm about to do the flip the paper trick. Right? And I'll show you guys that one leads to the other. Okay. Now, the original function was an upward parabola. It looks like it's been shifted to the right 5, and then it's vertically squeezed. So 2 this is like 0.4. Okay. So if I go 1, 2, 3, 4, 5, like right here, okay, and it's a real flat curve. So yeah, I wonder what the y-intercept would be. Let's find that too. Well, if I plug in 0 for x, this would be price is 25. 25 over 5 is 5 times 2 is 10. I think this should cross up here at 10, right? This is like 5. Okay. So my function, my parabola looks basically like this. It's probably a pretty good representation right there. Okay, that's the original function. Okay. Now I'm going to make this really bold with marker. Okay, so it really stands out. Okay, so pretty much like that. It's got a parabola. Okay. And then I know if I flip this over this 45-degree line of y equals x, should be right here. This is y equals x. Okay. And I look through the paper that could represent the function. Right. Alternatively, the function could be represented by this expression right here, okay, where I have some square root plus 5. Oh, okay, okay, keep in mind my axes are a little bit skewed. Okay, so here's 5 on this axis, 5 on this axis looks really short. Okay, so my y-axis is kind of squashed just to fit on this paper, but 5 is like right here. So if I take the square root, blah, 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 right? The square root up at 5 looks basically like this. Okay. And then, yeah, you know what? My 45-degree line is not even 45 degrees anymore. Okay. Right. Because the 0.55 is actually here, isn't it? Yeah. Okay, so this all comes from skew my axes. Oops, sorry about that. Okay. So this is y equals x right here. That's actually the 45-degree line sort of then, if I flip it over. Because this also goes through the point. If I plug in 10 here, 50 over 2 is 25. Yeah, that would give me bottom half of this parabola, right? So I'm doing this in pink. This is my inverse relation right here that I just did in pink, like that, right? Now, if I flip this, watch this blue line should turn into basically the pink line again. Keep in mind my axes are skewed, so decide that. So take the two ends of my y equals x line, which are right here, right here. Right? Flip the paper, right? And oh, look at that. Right? Here's my new x-axis, my new y-axis, right? And then this parabola takes the new place, right, of looks like that. So there's. Okay. So is the inverse a function? No, because of this plus or minus right here, right? Unless Alex prompts you to say like, well, only cut off half of this makes it a function, you could get rid of that minus right there, and it would just be the top half, and that could be a function. But okay. Great. Number two is a table of values. Let's take a quick peek at that. So for every x value, there's some corresponding y value. Now, for every y value, does it correspond to one x value that stays at 1 to 1? Well, no, because I see a couple places failing. So at where the y value is 4, the x value could be either 4 or -4. I'll draw that out. Okay. And also, when the y value is 2, right? So if I plot this out, here's x, here's y. 1, 2, 3, 4. 1, 2, 3, 4 that way. 1, 2, 3, 4 that way. Right. So we got 0, 0. We got let's see, -2, 2. Oh, I see what this is going to be. It's going to be an absolute value expression, isn't it? Yeah, yeah, that's exactly what this is. Okay. Right, so that's one of these V-looking graphs, isn't it? Or I'm kind of assuming that. All they gave us for these 5 points. 1, 2, 3, 4, 5. But you can still say that the inverse would not be a function. Okay? Because the original graph fails the horizontal line test, which itself doesn't make it not a function. So this is still a function because it passed the vertical line test. Okay? But when I flip the x and the y, you get a conflict here and a conflict here. Okay? So let's try that. If I flip the paper, yeah, can you guys see through the paper? See how this would now, here's my new y-axis. Okay? See how these points would fail the vertical line test. Right. So yeah, this would be not a function. Well, its inverse would be not a function. So f inverse x is not a function. There you go. Number 4. Find the inverse of this. Right. And well, here, anytime you have a straight line, its inverse will also be a function. Okay. So let's do some examples here. Yeah. I can either solve this out algebraically or do the flip the paper trick. Okay. Here, this time I will definitely scale my axes the same so that more obviously works when I flip the paper. So I have -2 here, 1, 2, 3, 4 here. It's -2. Okay. And the original function goes through these points. Like that. Okay, this is my original f of x right here. Okay. And they're saying that's equal to 2x minus 4. Okay. Here's my 45-degree line at y equals x right there. Okay. And I wonder what's the inverse going to be. Well, I can try that here. So I can say x equals 2y minus 4. See, all I did was I swapped the x and the y. Okay. So I'm solving for the inverse and pink ink here. And then solve for my new y. So add over 4. So 2y equals x plus 4. Then divide both sides by 2. So y equals 1/2 x plus 2. Okay? And that right there is your inverse relationship. So did wait a minute, why did they say -4? That's not that line. That's a misprint. Well, how did I not catch that? That's okay. Here, we can fix this. Because this is +4. See how it's crossing +4? Okay, no, they got the slope right. It's still up to over 1. Guys, this is +4. Oops. I don't know how I didn't catch that. Right? So that means that this would be plus, which means you subtract over the 4. That would make this minus, which then this comes out to actually minus. Okay. All right. All right. I catch that at some point. Oops. Got a little typo there. That's all right. Right. Oh, well, heck, dude. So this inverse is going to cross at 0, -2. Let's see, there's the y-intercept at -2. It has a rise over run of up 1 over 2. So up 1 over 2 there, up 1 over 2 right there. Right. And then okay, straight line relationship. And oh, look at that. Look how all these lines converge at the same point. So where the original function and the inverse function cross each other, they cross each other right on that 45-degree y equals x, just like I did before. So here's your f inverse of x right here. You go like that. Yeah, it's all work, right? And then final test. If I pick up the paper and I hold the paper's at the end of this y equals x line and I flip it over that, do these two exactly exchange places? Does this pink take the place of this black and the black take the place of the pink? All right, let's see if it does. Oh yeah, it sure does. Here, I'll make this more obvious. Break out the marker. Right. So here's my current y-axis and my current x-axis. But those are about to change when I flip the paper. This will become the new x and this will become the new y. Right? And then my original function, make that fold. My inverse function, make that fold. Okay. You guys, when I flip the paper, the picture should look exactly the same, right? Is it because these two are just going to swap places. Right? That's all they're going to do. Right? And yeah, that is the same picture. Right? So this is my inverse, right? And this is my original function. Right? Now they just swap places. Yeah. Here's my new x-axis. Here's my new y-axis. Yeah. Sure. Same picture. Yeah. Just like that. Next. Number 7. Okay, so find the inverse of each function, then graph the function and its inverse. Oh, here we go. If necessary, restrict the domain to the inverse so that it is a function. Yeah, right. So if we get a sideways parabola, maybe we'll just cut off the bottom half of it to get a function. So I have f of x equals -2x plus 1. Okay? And to find the inverse, first, I'll swap the x and the y and solve for the new y, like that. So let's see, subtract over 1. So -2y equals x minus 1. Divide both sides by -2. So y equals -1 half x. Now, -1 over -2 is +1 half. Right? And that right there is the inverse function. So right there. Okay. So here's my original function. Okay, and here's the inverse. Okay, and let's graph both of those. And then try to flip the paper trick and see if it's all the same thing. Okay, of course, this will work. Okay, so got x dot y. 1, 2, 3, 1, 2, 3. 1, 2, 3. 1, 2. Yeah, it's pretty close. That should work. Okay. So -2x plus 1. Well, here's my plus 1. Now -2x, that's down 2 over 1. It's right here. Down 2 over 1 is right here. 2 over 1 right there. Right. So here's the original function. Here's the original function. That right there is f of x. Okay. Now the inverse function has a y-intercept at 1/2. Or maybe I'll switch to pink. Right, 1/2. And a slope of -1/2. So down 1 over 2, right there. Right. Down 1 over 2, right there. Or 1 back 2, 1 back 2. Okay, I think all those points should lie. Yeah, all on a straight line. Zip. Right there. There's your inverse function. Right, so here's f inverse of x. Okay. Now, are those really flipped over this y equals x line, like I'm here? This is basically y equals x. Yeah, they do cross all at the same point, where they cross each other. They also cross at y equals x. That's true, right? Yeah, I think they will. I think if I pick up this paper and flip it, that the positions of those two will just change places. Okay? And my x and y axis will change places. So I'm putting that in dark marker here. Make it more obvious when I flip the paper. Okay? Okay, so here's my original function. Here's my inverse function. Like that. Okay? So axes, original, inverse. Okay. Let's see. When I flip the paper, does it create an identical picture? When I flip the paper, okay, that's to say my original and my inverse function will swap places, but otherwise the lines will basically look the same. So I'm flipping it over this 45-degree line. Zoop. Yeah, that's the same picture. That's the same picture right there. The line, isn't it? Yeah. Wing, wing. It's the same thing. All right. That's pretty good. Okay, number 14. Ah, here's our parabola example. 14. They're giving us an f of x is x squared plus 4. Okay. They said restrict the domain so that the inverse is a function. Well, another way to say this is, can I rewrite this to make this 1-to-1? So here, I'll get a graph going down here. I'll leave some space to do the algebra. Let's get a graph. Okay. So this look like, okay, x, y, let's go 1, 2, 3, 4. This point there, 1, 2, 3, 4, 2, 3, 4, 1, 2, 3, 4, something like that. So 4, 8, 4, 8, something like that. Okay. Now, if I graph the original function, x squared plus 4, that's just a regular parabola as y equals x squared, then shifted up 4. Right? Or you can make a table of values. You could always do that. If you plug in 0, you get 4. That's this point out here already. If I plug in 1, 1 squared plus 4 is 5. So the point 1, 5 exists. If I plug in 2, 2 squared is 4 plus 4 is 8. So this point here. And if I plug in negative values, then the negative values squared also become positive. So -1 being squared is positive 1 plus 4 is 5. So that could be this point here. And then -2 being squared plus 4 could be this point here, right? Right. But I want to be careful and restrict the domain so this is only 1-to-1. And maybe I'll just pick the right side of this, okay, the right side. And this left side, well, it could be there, but I'm going to dash it. Okay? Because if I had that there, then it would fail the horizontal line test, which means my inverse would fail the vertical line test. Okay? So I'm going to restrict domain to x such that x is greater than or equal to 0. I'll just do that. Right. So I'm just taking the right half of this parabola. Right. Now let's find the inverse. I'll change the pink ink for inverse. So I'm swapping my x and my y. All I did was f of x became x became y, right? And then solve for y. Right. So subtract 4. Y we're solving for squared equals x minus 4. Take the square root. Y equals the square root of x minus 4. Okay. And that is your inverse function. Inverse. Okay. Okay. Oh, notice I am calling this a function, okay, because I'm only going to take the top half of this. See, if I did plus or minus, it would no longer be a function. Okay. Now, I know what a square root is. Square root looks like this type shape. Okay. And then if you have a -4 inside, the root doesn't shift the whole thing to the right. Like, for example, if I plug in 4 for x, 4 minus 4 is 0, square root 0, 0. Okay, so that's this point right here. But if I plug in 5, 5 minus 4 is 1, square root of 1 is 1. So that's this point here. Now, if I interpret that as plus or minus, you could get this point down here. Be careful about that, because that would make it not a function. What if I plug in 8? 8 minus 4 is 4, square root of 4 is 2. And if I interpret it -2, that could be out here. Okay. So if I only take the top half of this, then it passes the vertical line test, so it could be a function. Okay. And I'm going to dash the bottom half because I'm throwing all this out. Okay. Now, if you compare it, the original function and the inverse function, yeah, I can see, just eyeballing it, that those would be flipped over this y equals x 45-degree line, y equals x right here. Okay. And in fact, I made the solid parts corresponding also. Right? So I think this part would mirror to this part, and this dash that I'm throwing out would mirror to this dash, which I'm also throwing out. Yeah. Okay. So let's see. Does that work? Okay, let's make this bold right here. I'm keeping that. Make this inverse bold right here. Keeping that. Okay. So here's my f of x. Here's my f inverse of x. Okay. And then let's get the axes so that they also show through when I flip the paper. So I'm going to flip the paper. Whoa. Okay. Okay, pretty close. All right, so pick up the papers at the ends of the y equals x line right here, and flip it over, and I should get the same image flicker through. Yeah, that's the same picture. All right, so here's my, well, what was the inverse, and here's what was the original. And now they just swap places. Yeah, just like that. There you go. And we got the correct domain restriction on the original, so that the inverse is still a function. We got it. We got it. It's all good. Yeah. You guys notice too that the domain and range swap places. So this has a range. Here, I'll write this out. Range, going back to the original, well, it starts at 4 and then goes up. So it's y such that y is greater than or equal to 4. Ooh, something like that. Okay. Now, the domain of the inverse is 4 to infinity, which looks like the range of the original. And the range of the inverse, well, I'm going to cut off at 0 and just go 0 and up, matches the domain of the original 0 and up. Yeah, that's a domain and range also swap places. We'll see that with inverses. Number 19. Determine whether each pair of functions is inverse, right? Yes or no. Right. I'm going to put it through that test. Is f of g equal to g of x, which is equal to x. Right? So they're giving us f of x is 5x minus 5. And they're giving us g of x is 1/5 x plus 1. Right? Now the examples we were doing from the book. Okay, well, I showed you some that worked. Right? But then a couple of them did not. That was a little disappointing, but yeah, we're going to find out. Right? So is f of g of x equal to, so put a little question mark here, this is our test, g of f of x, which should just be equal to x. Right? If this is true, then these are inverses. And if it's not true, then they're not. Right, so let's try it. So f of g of x, what is that? Well, f of something is 5 times something minus 5. Right? That's the structure of f of something, right? 5 times something minus 5. But that something is no longer x. It's g of x, which is itself 1/5 x plus 1. That's what goes there. That's f of g of x. So let's clean this up. I'll distribute this 5. So 5 times the fifth x is x. And then 5 times 1 is 5. Then minus 5. Oh, look at there. X. Bing, 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 bing. I think these two are inverses. Now, to make ultra sure, I'll try it the other way around. What is g of f of x? I mean, it should work both ways. Right? So g of something is a fifth of that something. And then plus 1 at the end. Right? But the something is no longer x. It's f of x. Right? So this one, which is 5x minus 5. So distribute the 1/5. So 1/5 times 5x is x. 1/5 of 5 is 1 plus 1. Oh, yeah! Ding, 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 ding. That worked too. Worked both ways. So, yes, inverses, inverse relationships, right? Inverse functions, right? And if I graph these, then I could flip the paper over a 45-degree line and they would also line up too. Right, 23. The formula for the volume of a right cylinder cone with a height of 2 feet is 2/3 pi r squared. Determine whether r equals root 3v over 2 pi is the inverse of the original function. Okay, here, I'll give you guys a little picture and then we'll set apart on this quest. Okay. So what if you had like a circular base? I'm looking at this kind of from the side. Okay. Right, and it goes up into a cone shape, right, like this. Okay. Now, anytime you see anything come to a point like that, like in this case, a cone or maybe a pyramid, like Great Pyramid of Giza, you can find a volume by taking the area of the space here. Now, here's the radius. Okay, so it's just the radius. Okay. Um, so the area would be pi r squared, right? Multiplying by this height and then dividing by 3. Right? So again, anytime anything comes to like a single point, it's 1/3 of the 2D base times the height. Okay? Which, well, here, I'll spell it out for you guys. Okay. So base times height, that could be pi r squared for the circular base, which I'm hatching right here, okay, times the height, and then the whole thing's over 3, or put it 1/3 in front, something like that. Now, they're plugging in a 2-foot radius. Okay. So they did that ahead of time. Okay. So they're saying given radius equals 2. Um, yeah, but that's sorry. Height is 2. Okay. Whoops. Sorry. Height is 2. Right. Okay. We're good. We're good. Right. So where the h goes, I'm just going to put a 2, and that's exactly what they say. Okay. So volume as a function of radius, again, given height equals 2. Okay. So I got 2/3 pi r squared. Right? Okay, so we're good. Right. Now, what if you wanted to go the other way around? And maybe you fill this with water, and then pour out the water and measure the water. So now you know the volume. It's like, I wonder what is the radius of the wide part of the cone, right? Now, they're saying supposedly it should be radius as a function of volume is square root 3 volume over 2 pi, right? And if this is true, and this is also true, I know that, right, then they should be inverses. And if you take one function of the other function, it should just equal, well, it should equal out. So what is volume? Is a function of radius as a function of volume. I should just get v out of this. Let's see if I do. Volume of something is 2/3 pi, right? Again, given a height of 2, that's all embedded in this thing, of something being squared, right? And the radius being squared. But the radius as a function of volume is this funny looking expression, root 3v on 2 pi, right? So if I square root, those cancel out. I get 2/3 pi 3v on 2 pi, and equals v. Bing! Yep, that's good. What if I take radius of volume as a function of radius? I should get radius out of this. Let's see if I do. Well, the radius of something is square root of 3 times something over 2 pi. And the something here is the volume, which in terms of radius is 2/3 pi r squared. Right? So that's the square root of r squared, which is r. Ding! Yeah, so it worked both ways. So yes, inverses. Yes, inverses. Right? So now you can find volume as a function of radius, or if you know the volume and you want to find what the radius is, you can use this other expression, which is the inverse. It all works. It all works. Find the inverse of each function, graph the function and the inverse. If necessary, restrict the domain. Okay, we've done a bunch like this, so yeah, maybe I'll do this a little faster. What if f of x equals x plus 2? Well, for the inverse, I can do x equals y plus 2 and solve for y. Right, so just subtract over 2. Right, so now f inverse would be x minus 2. Right. Now what do these look like graphed out? X, y. Okay. Now x plus 2 is just y equals mx plus b, get plus 2. Has a slope of 1, looks like this. There's your f of x. F of x equals x plus 2. Okay. Right. F inverse should be x minus 2. So got minus 2, and then the same slope as before, right, parallel to that, like that. This is f inverse of x equals x minus 2. There. Yeah. Both of those are mirrored from each other over this y equals x line. Here's y equals x. Yeah, this is a mirror. Is that? Here, what if I do flip the paper trick? If I flip the paper over this 45-degree line, does it give me the same set of graphs? Yeah, that's the same thing right there. It's the same thing. It sure does. Yeah, so those are inverses. At 29. All right, so here's one that looks more like a parabola. I get f of x equals 1/2 x squared minus 1. Well, I remember last time I ran into this, I did restrict the domain to x such that x is greater than or equal to 0. Okay, and same thing here. I'm just going to use the right half of this parabola so that when I take the inverse, I'll get the top half of the parabola and it will still be a function. Okay, let's find the inverse. Inverse. I think I should be switching to pink for the inverse. I'll do x equals 1/2 y we're solving for squared minus 1. Okay, so add 1 over. So 1/2 y we're solving for squared equals x plus 1. Multiply both sides by 2. So y squared equals 2x plus 2. I went ahead and distributed the 2. Take the square root. So y equals the square root of 2x plus 2. Right? Which, by the way, is the square root of 2x plus 1. You could also think of it that way. Right? That is your inverse function right there. Okay, so let's try that out. Okay. What if I graph the original function and the inverse? Okay. And this inverse would only be the positive half. Okay, so just the plus part right there, just the plus. Okay. So does this all work? Let's see. Right, so x, y, let's go 1, 2, 3, 4. 1, 2, 1, 2, 3, 4. 1, 2, something like that. I think that should fit. So 1/2 x squared minus 1. Well, minus 1 is right here. Okay. If I plug in 1 for x, this is a half minus 1, which is negative half. Well, if I plug in 2 for x, 2 squared is 4, divided by 2 is 2, minus 1 is 1. Okay. And then I could get this point and this point, but here, I'll dash this off because I'm not actually including it. Okay. But I am going to include everything in my domain, which is x is greater than 0. That's like that. Okay. So that's this part right here. Okay, so there's my original function. Right. Now my axes are scaled the same. Right, so nothing's too crazy. Right. Here's my 45-degree line. Y equals x. Right? I bet these graphs intersect right, bam, right about there, wherever that would be. Right, so how about my inverse? Well, if I plug in 0 for x, it's 0 plus 1 is 1 times 2 is 2. Right, and then the square root of 2 is like 1.414. That's right out here. Actually, look at my original function. It looks like it crosses the x-axis about 1.414. So yeah, I think we're good so far. Okay. What if I plug in 1? 1 plus 1 is 2 times 2 is 4. Square root of 4 is 2. So that's this point here. What if I plug in, what else could I plug in? 2, 3, looking for a good number. How about 5, 6? Well, yeah, okay, here, let's get a decimal value. Let's plug in 2 and see what happens. So the square root of 2 times, no, 2 plus 1 is 3. So the square root of 6 is like 2.45 about. So if I plug in 2, I get like 2.45 is right about there. Okay. Okay. Yeah, I do see that these this kind of look basically like this, isn't it? Yeah, there you go. Right, and it crosses right there. Okay, so I think that's pretty good. Pretty good. Okay. Yes, these cross over each other. Let's see. Zoop, zoop. Yeah, about like that. Like that. Right. 43, sketch a graph of the inverse restructure. Yeah, okay, so I'll just do a couple more with you guys. These two right here. Actually, maybe I'll throw in this last one too. But let's do these last three right here. Bing, bing, bing. Do those. All right, so graph the inverse of each of these. Well, I've been showing you guys a cool trick you can do with just reflecting over the y equals x line. So x, y. Right, so 43, the original function is basically a quarter of a circle. It looks like. I'll blow it up a little bit bigger. Okay. So if this is your f of x, right, then I know the inverse would just reflect over this line, or you could reflect it point by point if you wanted to. Okay. So instead of the point, if this is the point 0, 1, I know the inverse would be the point 1, 0, which would be right here. 1, 0. Okay. If this is the point -1, 0, I know the inverse would be 0, -1, which is like 0, -1. Okay. And if this is like 0.7, so negative 0.7, 0.7, maybe like that. Yeah, 0.7, -0.7 is right here. Okay. So anyway, it's going to create this, should switch to pink for the inverse. Let's do inverse in pink. Here's your inverse right here. F -1x. Right? And just like I told you guys, it would reflect right over that 45-degree line. Or if you hold the paper against that and flip it over, it creates the same looking graph. Look at that. It's the same thing up inside. Same thing. Right? 46. Alejandro is a personal trainer. For his clients to gain the maximum benefit from the exercise, Alejandro calculates the maximum target heart rate using the function f(x) is 0.85 to 20 minus x, where x represents the age of the client. Okay, so if someone comes in and says, oh, I'm 47 years old, what should my heart rate be to optimize my exercise? Well, you just plug in 47 here, right, and it'll tell you the optimal heart rate. Find the inverse of this function and interpret its meaning. Okay, well, see, they're looking for the target heart rate as a function of their age, but what if you turn this around? What if you had somebody's data and you're looking at their heart rate and saying, this would be really good data if you were what age? And that is how I would interpret the inverse relationship. So let's try it out. All right, so this is 45. Right. I'm going to say y equals heart rate and x equals age. Right. Right. And I'll use those as stand-ins. So we got y equals 0.85 220 minus x. Right. So it looks like the older you are, you're subtracting off more and more. Maybe you want your heart rate to be slower and slower. Right. Now the inverse is I could just solve for age in terms of optimal heart rate. So if somebody tells you your optimal heart rate, say, huh, I wonder what age you ideally would be for that given heart rate. Well, that would be the inverse relationship. So I'm just going to solve for x. So divided over 0.85. So 220 minus x we're solving for equals y over 0.85. Now the meanings are still the original meanings. That's why I'm leaving x and y as their values. So y is still heart rate and x is still age. But now I'm just solving for x in terms of y. That's still an inverse relationship. And then here, I'll negate both sides. So x we're solving for minus 220 equals negative y on 0.85. And finally, add 220 to both sides. So the optimal age given a heart rate would be 220 minus that measured heart rate over 0.85, like that. So there's your inverse. So this is the age, maybe an optimal age given some measured heart rate, like that. And that's the inverse. Look at that. All right, and last one, 46. Graph the inverse of the piecewise function shown. Okay, so all I have to do is swap the coordinates. What's x and y becomes y and x. 46 there. Right. And that'll take care of it. Okay. So first I will copy down exactly what's shown. Here's x, here's y. Okay. The scale is 2, 3, 4, 5, 6. Okay. 1, 2, 3, 4, 5, 6, 7. Okay. 1, 2, 3, 4, 5, 6, 7. Something like that. Okay. 1, 2, 3, 4, 5, 6, 7. Okay, I have to go negative 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7 would be way back here. Looks like that. Okay, so we got the point 2, 2. That's right there. 2, comma 2. Then it's a straight shot to 3, 4, 5, comma 1. This is 5, comma 1. Okay. And then that goes to 6, comma 0. 6, 0. And that goes down to 7, negative 7, which is at this far corner right here. 7, negative 7, like that. Okay. Okay. Now they're saying it's a piecewise because you could say, well, on this domain, it's this straight line. And then on this short domain, it's this short line. And then on this domain, it's this line, right? Okay. So it's all choppy like that. Okay. So I just copied what they had, just blew it up. Okay. Now I'm just going to reverse what's x and what's y. So 2 and 2 reverse is also 2 and 2. So that fits there. 5, 1 becomes 1, 5. Okay. 6, 0 becomes 0, 6. And 7, negative 7 becomes negative 7, positive 7. That's right up here. Wait, pretty close. Okay. So the inverse function, I think, would look like this. Boink, boink, boink. Like that. So there you go. If this black line is f of x, then this pink line is f inverse x. Like that. Yeah, that's it. Yeah. All right, and let's do the flip the paper trick, and then I'll wrap up this video recording. So let's make a 45-degree line where y and x would be the same. Y equals x. Okay, yep, they definitely also meet each other on that line, just like the past examples I've been. Okay. I'll pull up my marker to make this really bold so that when I look through the paper, it'll be easier to see. Okay. So my current y-axis is about to become the x-axis when I flip the page, okay, and vice versa. This x-axis is about to become the y-axis. Okay. And then these piecewise functions, well, make those real bold. Here, put your hands best I can. Boink, boink, boink. Basically does that. That's the original function. And then the inverse, I'm planning does something like this. Yeah, you guys see some symmetry to this, right? About like that. Okay, So when I flip this paper over this y equals x line, it should create exactly the same graph on the other side. Oh yeah, it's the same thing, right? You also could have found it that way. Like if you were given an original function and you have no idea what the inverse looks like, you can just draw the original function and flip the paper, and it will tell you what its inverse looks like, and you're seeing it right here. Right? So it's the same thing. Same thing, same thing. Ah, there you go. And that is a wrap on 6-2.